Last minute stragglers. So thanks for getting started promptly. We have 3 exciting talks this morning, and so I want to make sure we have time for the speakers. Just to start with some announcements, you heard about Allison yesterday, so I won't repeat that. But anyone who has concerns about this can talk to me or talk to Allison directly. Just to remind you, we have both the group photo today, which will be at 5:30 outside the pool. Please be there, please be blue, and please wear a smile and all sorts of other things that are good for pictures. And as mentioned here, if there are any people with accessibility issues, let us know and we'll make sure we can accommodate that. There is a reception for all registered participants this evening, and we'll start at 6:30 in the last territory and courtyard, which you can find on your hotel maps. It's about a 5-minute walk. And your badge has a ticket in it, which is good for 1 drink. Additional drinks cost real cash. Just to remind you about the unconference that will be held tomorrow afternoon. So there's a bulletin board outside you can see, and all ideas, any ideas and all ideas are welcome. Just write up a little post-it and put it on the board and assemble people, and we'll try to get that going together. And then 2 announcements from LSST Corporation. Many of you are aware of the Data Science Fellows Program. So there's another round, and the application deadline for that, particularly students should pay attention to this, is August 22nd. There's a web address to do the apply, so make sure you get your application in. And then we announced this at the reception last night, but will be the first LSST at Asia meeting. Will be held in Sydney, Australia. This coming May, and we'd like to encourage attendance at that. The LST at Europe meetings that we've held, there have now been 3, have been extremely successful at engaging our international contributors. And then finally, there will be a session reviewing the breakouts, which is scheduled for Friday. So in every one of the breakout sessions, please appoint someone to write up 1 slide, which can be uploaded and then be prepared for the 1-minute summary talk of the breakouts that we can do in the plenary. So ensure you have someone doing that, and that it's uploaded in time in advance of Friday. Okay, so let me start with our featured talks today. We're delighted to start with Professor Barry Parish, who's the Linde Professor Emeritus of Physics at Caltech. Barry is a distinguished particle physicist who's been involved with a number of major experimental facilities over the years, including the SSC, I guess, and then the ILC. But most recently, he's attracted a lot of attention because of his role in LIGO, which was crucial to making LIGO successful and eventually leading to the first detection of gravitational waves. For that, Barry was the co-recipient of the 2017 Nobel Prize in Physics. And he's going to talk to us today not only about LIGO, but how LIGO emerged from a facility towards science and what the lessons learned are for LSST. So please welcome Barry Parish.
Can you hear me now? Yeah. So when Steve asked me to give this talk, he used the words he just used, lessons learned from LIGO. I'm not sure there are any lessons learned from LIGO, so I changed the title. I'm going to talk about the period that we all kind of think should just happen. You construct something, you build it, you've thought about it, you've worked on it hard. During construction, you know what you're doing. You have a critical path, you know how close things are to a critical path, and you know how to do things. And then you bring it all together, and there's some period of time you give to test things and do science, but it's a much less linear problem. And I think for us, the most common word used during that period was workaround. So basically, I can't talk about how to do workarounds, but basically that's the most common thing we did. So I'm going to tell you a little bit the story of this bumpy road for LIGO for whatever use it is. But a second reason, the real reason I decided to accept his request that I give this talk is that I've become the chair of what's called the AMCL. And this gives the chance for me to be introduced to the rest of you because I'll be doing that. This is the web page on it. What's interesting is that the charge of this committee is a mix. It's both oversight and advocacy. I'm not sure I've ever been on a committee that was the mixed charge that it has. But I think we basically serve the purpose for aura and overall of a committee of people. You can see the lists here, I'm not going to go through them, of people who are quite experienced in a lot of the areas most of the areas that LSST touches, to look and try to help. And at least my personal role as chair, when I become chair, which is next month, is to try to see in what ways we can help. This project is over-reviewed, so we don't have to deal with trying to duplicate everything that's done in the reviews, but to try to help. Anyway, let me go on to the story of LIGO, because I've only got 20 minutes or so. First, for those of you that don't know, I'm not going to talk about the science, and I'm not going to talk too much about the project, just enough to talk about this middle period. But let me just say a few words so you know what we have to do, what the challenges are. And I'll try to point out why I think there is almost no lessons to be learned, because we basically, in contrast to LSST, can't build something that we know we can turn on and use for 10 years. It just doesn't work that way for LIGO. We're learning as we go along. So gravitational waves themselves come from some sort of event in the universe, and they're ripples in space-time itself. They're not like photons that go with electromagnetic waves. Space is very stiff. It gets stretched and squashed by gravitational waves, but not very much. The amplitude is actually, this is the magnitude of the strain in general relativity is of the order of 10 to the minus 21 for most sources that we can envision. So that's a tiny number. I'll try to make you understand how tiny and why it's a challenge. That translates itself directly into what you measure experimentally, a change of length somehow of something that got its length changed by the stretching or squashing of space and time. So you can imagine a ring of free masses of radius L, and a gravitational wave goes through it. It's going to stretch it in one direction, squash it in the other by an amount of 10 to the minus 21. That's proportional to delta L. So delta L is little h times L, and that's what you have to measure. Now, to again make the experiment as simple as I can possibly make it, the challenge is we use interferometry. The challenge is to do two things, really, and that is to somehow reduce what's normally a problem by a factor of 10 to the 12th. We want to measure a strain of 10 to the minus 21. That corresponds to a length in an interferometer the size of LIGO of about 4 10 to the minus 18 meters, a small fraction of the size of a proton. And to do that, we have to control the length that we measure in two factors. One is anyone who's using an interferometer. We have to basically split the fringe by a factor of 10 to the 12th, an unheard of amount. And secondly, experimentally, we happen to live on the Earth. We don't care about the Earth. We have to isolate ourselves from the Earth. And we have to handle that by a factor of 10 to the 12th. That's also a very tiny number. Those two tiny numbers are what dominates the LIGO design. So we built LIGO. I'm not going to go through any of the real technical details of that, just mumble at them. We have two LIGOs. That's for reasons of both being able to be sure of what we see and to have a handle on directionality of where gravitational waves come from. The instruments are identical. The topography is totally different. One is swamps in Louisiana and the other is high desert in Hanford, Washington. We started building about 22 years ago. The real factor, I think, that makes it different from LSST is it's all evolutionary. Probably the most important thing I think that I did at the very beginning was convince the NSF to spend more money than they first intended to on the infrastructure itself, trying to make an infrastructure which costs the majority of the money, that we could evolve the instrument in time without having to rebuild the infrastructure. And that meant bigger chambers, bigger vacuum pipes, a lot of access, and so forth and so on. So we started constructing. Even then, there was a science decision. Do you orient the two interferometers parallel to each other or at 45 degrees to each other? That was a big debate in the 1990s. We decided to do them parallel to each other. You know that because when we saw gravitational waves, put one plot on top of the other and they looked identical. The reason why you might want them at 45 degrees to each other is like in electromagnetism, gravitational waves are polarized, and you can get a handle on the polarization if you have them at 45 degrees to each other. But then you can't lay them on top of each other if the polarizations affected the waveforms. This is just a couple quick pictures just to show you what we built. We built the biggest high vacuum system in the world, bigger than CERN in high vacuum. It's 1.2 meter diameter pipes, 16 kilometers of it. We had to do it in place. Very large, and you can see for evolution why there's so many ports and so forth. Very large tanks to put mirrors and lasers and so forth. Great big gate valves on the sides that you can see to isolate it from the large vacuum. Very different topologies, but identical instruments. Just quickly, we're limited by all kinds of things. This is a simple picture of an interferometer, but our requirement to get the resolutions that I talk about require the high vacuum because we worry about gas scattering, making longer path lengths for the photons that scatter around and don't follow a straight path. We need a more precise laser by a lot than the laser in my hand. So we have to stabilize it in wavelength, amplitude, and pointing, and by all kinds of locking it to cavities and so forth. We have to isolate ourselves from the ground, one of the biggest problems, by a factor of 10 to the 12th. We have to worry about the fact that we're working at room temperature. In the future, we'll be cold, but at room temperature where there's Brownian motion in the mirrors themselves. We have to worry about the fact that if we bring in enough photons to get good statistics, then we put radiation pressure on the mirrors. We call that quantum noise. In the end, if you put all those noise factors together, we get a curve that might start looking familiar to you if you've ever seen a LIGO paper, and that is our noise curve follows the shaded area, where at low frequencies we're dominated by the shaking of the Earth, at high frequencies by shot noise, or for particle physicists by photostatistics, and in the middle range by the fact that we work at room temperature. And lurking below is all the things that I pointed to, like vacuum and so forth, that we have to keep below that. Okay, this is now starting to be what happens. So we built the first version of LIGO not trying to build the ultimate instrument in the 1990s, turned it on and made it an interferometer by about 2001, and then at that point it was the most sensitive one that had ever been built, so we set new limits on, not very good ones, on various astronomical sources. We took data for months, turned it off, licked our wounds, fixed what we learned, put in whatever we hadn't done before that we wanted to, and ran again. We did this for about 7 cycles or so till 2005, and then we got down to what we could calculate as the design ability. During that same period, we developed in R&D with the same people that built the original LIGO, the improvements to make the real version of LIGO that we wanted to make, and brought that to the NSF, and they funded it a few years later, 2008, and then we started building the construction project that I'll now come to. We understood what all those noise sources were below. I'm not going to describe that, so we knew kind of what we had to deal with. Our goal, this was the last final run for the original version of LIGO, where we learned everything that we needed to know. The little thin line was the design, so except at the lowest frequencies, we pretty much were along that. The two colors are just different optical configurations. One of them emphasizing high frequencies, one of them low frequencies, and that's as good as we were. We wanted to improve a factor of 10. That was the goal of advanced LIGO. At high frequencies, to simplify the problem, that's a higher power laser. At middle frequencies, it's better test masses and suspensions, better ability to handle thermal noise, and at low frequencies, better seismic isolation. That was basically the approach. In simple-minded, it was a complete rebuild and a new instrument, which I show here but won't go through. So we went through the equivalent of what LSST has done up till now, designing, building a comparable cost project that now had to come together. So I'll spend my last time on how we tried to bring this together using the word workaround at every turn. So there's a new laser. It's more complicated than the one in my hand. Fantastic, beautiful mirrors, which to the eye, these are fused silica, which to the eye is the most beautiful piece of glass you ever saw, but they're coated to reflect at 1060 nanometers where neodymium YAG laser emits. And a suspension system that now kept the suspension at the bottom, the beautiful mirror with no instrumentation on it, a multiple pendulum, where you try to control the position of the bottom mirror from above, which is tricky, but we knew how to do that. And a very fancy system of seismic isolation, where we include basically shock absorbers, like your car, only a little fancier, and an active seismic isolation, a little bit like the earphones you use on an airplane, to get rid of the ambient noise by measuring with seismometers the motion of the Earth and correcting for it by pushing back. That was the system, all to come together. So now we're bringing it together. So I'll start in 2012. We made the discovery of gravitational waves 3 years later. So it's about the same time period. These are now pages out of internal notes as we went along that I just picked to make the snapshot as we go along. So the first one you can see on the left is a bunch of things coming together. I'm picking on one piece of it just to make life simple, which is the input optics. This is the optics that enter the interferometer, which is not just the laser, but we condition it with a lot of optics before it enters the laser, so it's better suited to do the best possible interferometry. So here we see on the left kind of status of bringing together a bunch of pieces. Chambers, these are the big chambers you looked at. One of them's in, the second one it says it's installed, hasn't been used yet, and a table is ready to put the pre-stabilized laser on. We had, from the very beginning, a software mechanism which we use universally, which we use to track everything and everybody, and we had the discipline that anything that anybody found wrong appeared on this. So you'll see on the right entries of persons that found a grounding problem or any problem, and so every problem was visible to everybody on the project, basically in a common error issues register that was active and alive through the whole process. This is important certainly for trying to do workarounds, because you can easily think you know what to do in a workaround if you don't know the other parts. Each subsystem in terms of organization was led by a subsystem leader, usually who didn't live on site, very much like LSST. But we made a second on-site person responsible for that subsystem early, actually, before the construction was done and before it was delivered. So there were two main people, one local and one who was, well, two local because we have two labs, and one who was the designer. Plus, we had a much larger systems engineering effort in LIGO, system engineering and commissioning team, who were all the experts on bringing this together then. Second snapshot, maybe a year later, roughly, and I picked the piece which is the input optics, which I'm just picking for illustration, which is starting to bring all the pieces together into a sub-configuration, or a system that we'll test that you have to integrate together, which is the next common word instead of installation is integration of systems. So you can see, without going through in detail, there's different pieces, cavities, what we call mode cleaners, the interferometer elements, and so forth and so on. And that eventually comes together in something that looks linear, and that's a problem in anything that we draw together because of the word workaround. What do we do when we get stuck on one to continue the progress? And so we had a schedule. You'll notice the schedules, if you look at them in detail, are staggered for the two labs. That's because we put through all the expertise, highest expertise at making the thing work first in Livingston and then in Hanford, so that we didn't have to try to solve the problems in parallel. We also had a rather elegant system of making sure absolutely everything that was changed in one lab propagated to the other lab daily, so that we've kept the labs together, even though they're physically different. We then put together this subsystem. I'm now in 2014. You'll notice 2015 is when we discovered gravitational waves. This is 2014. It's a snapshot then of taking the input mode cleaner is what this is called, but it's basically a piece of that input optics. And it's all together and trying to work. Parts of it don't yet, and parts of it do. So we basically have this, and it's all available to everybody. The right, just without going through it, because I don't have time, is showing you that the input optics is much more complicated than just a laser, and that's being then put together. That's 2014. By September 2014, we started the final, what we call full commissioning of the total interferometer. Gave ourselves 1 year, which is what we took. And so this is September of 2014. We started in Livingston, and we got a first sensitivity curve that's shown here. And it's about half the distance that we measure and how far we could see neutron star binary in spirals as a way to measure how far we see. It was 36 megaparsecs. We ran it about twice that a year later. And that's the curve that we got at the beginning. And the reason I showed the one on the right is we identified a lot of what limits it. In this case, I picked on the fact that light finds various ways to scatter off different elements. And what we have to do is actually physically go and try to baffle those or fix whatever was causing the scattering itself. And those were long problems. On here somewhere it says something will be fixed by May or June, so they may take a long time, but we basically were diagnostically trying to make it work over this year. This then shows the timeline. Sensitivity is on the left, and the goal that we had given the NSF was that we would, for the first data run, be in between these two dashed lines. L1 means Livingston, Louisiana. And it came up over the year period. These are days. So over a 300-day period, it came up to well over the minimum that we said, and inside of it about 60 megaparsecs. We turned on Hanford somewhat later, and it went much faster, not surprisingly, because we had solved all the, quote, workarounds in Livingston. We had made fixes as we went along, even though we didn't try them in Hanford, and it went faster. In parallel with all this, we did the data acquisition, controls, and data analysis in a very testable way. This just shows two examples of the fact that we fed the data system. This is frequency versus intensity. And basically we fed different kinds of systems that might look like a pulse in the right one, ones that were a peak in some frequency in the left one, to make sure that they could be detected and handled in the data handling system. We basically, at this point, were here. The top one is the sensitivity that I'd shown you previously. We're now a factor of 3 better. You notice the two curves are right on top of each other, which means if we did things right, the interferometer in Hanford and Livingston perform the same, even though they're physically different instruments in very different physical locations. By the way, the vertical lines that you see are various resonances in the system, either electrical or mechanical resonances like you have in any system. They're about 1% of the area, and we notch those all out. They're constant in frequency and don't cause any problem. So we'd improved a factor of 3 everywhere. The goal is down here, a factor of 10. Again, the point that we're doing things in an evolutionary way. Some of the changes, like squeeze light, for example, are going in the present down period that we're in, And the idea was to be here by about 2021. But the first run was here. We gained a factor of 3 at low frequencies. That's a factor of 27 in rate because it's a factor, we measure in amplitude. So we see a factor of 3 further into the universe, and the volume was gained a factor of 27, which is significant compared to the years that we ran before. At low frequency, you'll notice we gained a factor of 100. That was the fact that we put in active seismic isolation. A factor of 100 is a factor of 1,000,000 in rate, and it answers the question I often get answered: how in the first week could we see black holes when we hadn't seen any in the first 7 years of running? In initial LIGO, we were a factor of 1,000,000 more sensitive than we were then. Okay, we also at the same time built the system to analyze the data. So this is the 2 schemes. We had 2 primary schemes. One that used calculated waveforms that use post-Newtonian calculations and coordinated numerical relativity. There's 200,000 of those. 200,000 are compared with every piece of data using matched filtering, which I show here by multiplying a signal, which is shown as the little one coming up, can be lower than the noise and builds up a signal that we see. That's the primary scheme that we use to look for known sources like binary black holes. That isn't the scheme by which we saw the first event. We actually saw the first event by our second pipeline, which is one that uses wavelets to look for a more generic form of gravitational waves. The reason we didn't see it in the template one was it wasn't quite working right at that point in time. This is the signal we saw on September 14th, 2015. It was big enough so we saw it without the matched templates. The next slide is important, and again, the fact that we did everything in parallel. This is the data that I showed you. That data is not handled in any way except bandpassed. What we did is throw away the frequencies outside of our frequency band that we looked at. Otherwise, it's not touched. There's nothing done in data analysis to these. This is the calculations of the general relativity, numerical relativity on a computer, which we had to develop during the same time period. If you subtract one from the other, you can see how well it fits, and that's the residuals that are here. This is in our first paper. So but basically, that's how well it worked at that point. So let me end by just, in this short talk, by just commenting on all these pieces that had to come together. In construction, we'd build all the hardware, and we had to install it, of course. And it had to be integrated into subsystems. We had to commission each subsystem. And then we had to do overall commissioning. So that's one set of activities. The second was the data handling. We have a whole group of people that through all running are there, and certainly through the commissioning were there, that looked at the data quality. I showed you a hint at things like looking at glitches. When they saw glitches like that or see them in the data, they have 2 jobs. One is to deal with the people that are the experts on the interferometry itself to see how we can get rid of such glitches. And the second is to deal with the data analysis people to see how the glitches that they're detecting might affect the data analysis. Second, we have a group that does calibrations. These groups, by the way, include many people from universities and users. The top one was almost all LIGO laboratory, which is equivalent of the project. The calibrations and sensitivity that we need for anything when we do the science, and that there's a group mostly of university and outside LIGO scientific collaboration people. And then we have several pipelines. The 2 that I mentioned, which are the main 2, is one that's unmodeled sources and one that's templates. Lastly, independent of the science itself, we have a data analysis activity that actively calculates numerical relativity. Here we have limitations, for example. If the 2 masses are very different from each other, it's really a complicated problem which we haven't yet solved. And we have a very complex problem of how you do parameter estimation. We see an event like that. How do we tell, and how well do we tell, and what are the errors on the objects that we see? And with that, that's a quick run through LIGO. Thank you.
So we have time for a few questions. Come up to the mic.
So the way you presented it, it seemed like there was a methodical series of steps to work through all the sources of noise and beat it down. What was the most surprising source of noise that you didn't anticipate beforehand?
Scattered light. We had taken a lot of paper-driven design ways of handling scattered light. Light scatters off everything. The mirrors they go through, molecules, any imperfections, and so forth. And we built a set of baffles inside the vacuum to handle scattered light. But the problem with scattered light, even today, is one that we are continually fighting. Paths that are found for light to not go in a straight line that, of course, then make them take longer to go from and are out of phase and going down one arm and the other arm. So I think the issue that we underestimated the most and continually are working on is scattered light.
Thank you for a very interesting talk. The LIGO project presumably had something like a science advisory committee that was working with it. And in the stage, as you described, the bumpy transition from construction to science, was there something that that science advisory committee was paying very close or particular attention to, or things that you wanted them to pay attention to make sure everything was smooth in that transition?
That's a very good question. We had a different structure. LSST, of course, has kind of a three-headed monster on top, or DOE and users. We had one, which is NSF. And independent of that, then instead of having something like the committee I'm running now, the AMCL, we had a self-appointed committee that the senior people, myself and others, appointed that were directly trying to help us. And I think that committee gave a lot of very important, I'm not going to pick out specific examples, but I think were very, very helpful in handling and pointing us at times when we're in this phase on the workaround problems, because we didn't always know the workaround, and often you're too close to the problem to get any perspective on it. And so I think they were very useful for us. They met every 3 months. AMCL meets, my model is AMCL should play some of that role here, but I doubt if the problem will be as severe. I think it's a more linear problem putting together LSST.
Thank you.
Yeah, so I'm curious to hear from you a little bit about how well did your time estimations for your commissioning effort match up with what actually unfolded in reality?
We promised on September 15, whatever it was, that was when we would run and we would be between those lines, which we were, which is interesting. So we made that. Probably because the construction went a little faster, and we were pretty adept at doing the workarounds, and we pushed a lot of, we don't have to make it run for 10 years, so we could push a lot of problems into the future. So we're doing things now that we thought we might do at the beginning. We pulled out some tricks that we were going to do later that we used then, but we made the first run. The second run, if I showed you, which I didn't, the first run we were supposed to be between 40 and 70 megaparsecs and 75% uptime. We were close to 70% uptime and 60 megaparsecs. The second run, we barely got into the region that we're in. The third run, which is coming now, I'm worried that we won't quite get there. 120 is our goal.
This question is related to the second question, which was about the advisory committees. Did you also have review committees that were appointed externally, and how did you work to make those as constructive as possible and as useful to you as possible?
I think we were over-reviewed, as LSST is over-reviewed. And I think it's a disease of big projects because of the accountability to the agencies in the government that we have so many reviews that they don't really have the perspective and distance that they should have. I think we were over-reviewed. I think LSST is over-reviewed. I think you'd Personally, I think if you put good people in charge and you have a good review system, you don't need to do as much as is done in today. So that's my own ranting, if you want. But I think in our case, we had one agency. It was NSF. They had a review committee that was a mixture of astronomers and physicists that were used to large projects. We got some very good and distracting, like happens in any reviews. You see, I'm not a huge fan of reviews. I think, anyway, I can't say anything more intelligent.
With such a diverse workforce across optical engineering to the physics to astronomy, did you have project and user-wide education in the technical details or about the science for everyone as part of this effort?
We really worked hard, and I did, because I came from particle physics and I came from outside at the beginning. And I think we worked hard, and we still do today, at really making one community. So we had people that came from, the present director is Dave Reitze. He came as a laser physicist. I came from particle physics, and we've worked really hard to make it one community. We have a very unified and accessible data document system, a very good system of communication, and all meetings are open to everybody, and we've really tried hard to make it not a set of discrete experts that have to be brought together. And we've had partial success at that. Success helps, science success helps, because then everybody identifies with it.
So our next speaker, while we're setting up, is LeAnn Guy. I hope many of you, if you haven't met her before, will have the chance to meet and interact with LeAnn at this meeting. LeAnn joined us in May of 2018 as the subsystem scientist for data management. She came to us from the Geneva Observatory, University of Geneva in Switzerland, where she was involved with the Gaia project, which is what she's going to talk about today. And she was one of the key people involved with Gaia algorithms and pipeline development, and interacted heavily with Will O'Mullane when he was at ESA in that capacity. So LeAnn is going to talk about Gaia, something to do with lessons learned. I forget the exact title.
Okay, thank you, Steve, for that introduction. Good morning, everyone. As Steve said, this hasn't come up. Oh, okay. There it is. As Steve said, I'm going to talk to you a little bit this morning about the Gaia project and some of the lessons learned and how I think that they can be of use to LSST. So on the 14th of September 2016, after just 1,000 days after launch, Gaia released its first intermediate catalogue. And this catalogue contained sources, it contained positions and magnitudes for over 1 billion stars, and it also included astrometric solution, parallax and proper motion for about 2 million sources based on a combined TICO-Gaia astrometric solution. In addition to these two main catalogues, there are also some smaller catalogues of variable stars, something like 3,000 variable stars, the Cepheids and Aha Lyrae stars, of which 400 were new discoveries by Gaia, and a small catalogue of quasars. And then, roughly about 18 months later, Gaia released a second intermediate catalogue, based on this time about 22 months worth of data. And the second Gaia data release really added a lot more sources, a lot more variety. It's a much richer data set than the first data release. And so this time we have something like 1.7 billion sources with positions and brightness. Parallax and proper motion are now provided with a Gaia-only astrometric solution for over 1 billion sources. And for these sources here, there's also corresponding spectrophotometry for the first time. The variable source catalog is now roughly 500,000. There's a small catalogue of solar system objects, 14,000 or so. And for the first time as well, median radial velocities were provided for 7 million objects. So the Gaia second data release was already a huge step on top of the first data release, which was already very impressive. And when Gaia first started out, it was billed as the billion-star surveyor. So a camera with 1 billion pixels, and it was going to survey 1 billion stars. And already, with only 22 months of data, Gaia has surpassed this to provide positions and brightnesses for 1.7 billion stars. And this is something that in Gaia we expect is going to continue now to only be improved upon, to add more objects with higher precision as the mission continues. So just a quick overview of some of the scientific impacts that Gaia has had so far. 800 refereed papers roughly have been put out since 2014, since the first Gaia data release. Based on Gaia Data Release 1, there's about 1,300 papers. I stress that many of these are non-refereed. You'll find these in the archive. And in the only 3.5 months since release, there's about 220 papers on the archive already. And so this is really impressive scientific harvest, I think, from these two catalogues. There are many areas of astronomy and astrophysics where Gaia is having an impact. In particular, an interesting one is the Kepler-Gaia combination, where Gaia is being used to pin down the properties of host stars to help with the Kepler project. White dwarfs, a complete census of the solar neighborhood, was very recently published. So the scientific impact is also very exciting with Gaia. Just a very quick overview of some of my roles in Gaia. I was, as Steve said, I was one of the main pipeline scientists in the variable star processing group, and I also acted as the liaison to the variable star scientific community within the Gaia Data Processing Consortium. I also worked on the spectroscopic data, providing the median radial velocities in Data Release 2. I was the release documentation coordinator, a very difficult job, probably more difficult than being a pipeline scientist. And throughout the whole project, I held many roles in QA testing, validation, and verification. And just these are some of the results and projects that I worked on that were published in the 2 Gaia data releases. So I'm not sure how many of you know details about the Gaia mission. I'll just take a few minutes now to talk to you about, just to give you a quick overview of the Gaia mission itself. So Gaia was a cornerstone mission of the European Space Agency. It was launched on the 19th of December 2013 from French Guiana, and it is orbiting around the Lagrange point 2. The nominal mission is 5 years, and there is a possible 5-year extension. The goal of Gaia was to produce the largest and most precise 3-dimensional map of the Milky Way, including, as I've already said, 1 billion objects, which has been surpassed, and providing micro-arcsecond astronomy and millimag photometry down to a limiting magnitude of 20.5 in G, spectroscopy and radial velocities for stars brighter than 16 magnitude. I forgot to point out that in Data Release 2, it's only for the very bright stars that we have radial velocities, and so this hasn't yet been achieved. Routine science operations started in 2014. This followed a 3-month delay due to some issues found in commissioning. Following commissioning, Gaia went into a mode called ecliptic pole scanning for 28 days, where the scanning law was focused on the 2 ecliptic poles. And after those 28 days, Gaia entered this nominal scanning mode, and then it has been running since the 21st of August 2018. And the Gaia data are released to the world through data release catalogues, which are world public with no proprietary period. Just a quick overview of the data processing flow in Gaia. Gaia observes the sky. The light enters the payload through 2 apertures onto the focal plane here. This shows you the focal plane where the data are processed on board. Gaia does not transmit images back down to Earth. It processes the data on board and transmits the data products back down over a link. We have about 40 gigabytes per day, comes down to 3 ground stations situated around the world such that there's 24-hour coverage of Gaia. This data then goes to the Mission Operations Center at the European Space Operations Center in Darmstadt, which then goes to the Science Operations Center in Madrid. This is where the first look and the initial data treatment of the Gaia data happens. Following that, this data is distributed out to a series of data processing centers across Europe where the data is processed and the science data products are produced by the scientists and engineers of the Gaia Data Processing and Analysis Consortium. These data products, once they've been produced, are built into release catalogs, which are then moved to the main database in Madrid and hosted at the Gaia Archive. And it's through this Gaia Archive here that any of you who've already worked with the Gaia data will have accessed the data. So just a few words about LSST and Gaia. There will be many overlaps scientifically with Gaia. There's a list of many topics here that where there's overlap, everything from stellar astrophysics, structure and dynamics of the galaxy, as I've already mentioned, exoplanets, where Gaia can pin down the properties of host stars, solar system studies. Gaia Data Release 2 already contains a catalogue of 14,000 solar system objects. In time domain astronomy, both Gaia and LSST will discover thousands of new variable sources. And in addition to all these very interesting scientific synergies, Gaia will also provide a very good and rich data set for doing calibration checks at the bright end for LSST proper motions and parallaxes. And so I'll just take a moment here to quote Željko, our project scientist. LSST can be thought of as Gaia's deep complement. I'm sure many of you have seen these figures before. In the photometry, the proper motion, the parallax, if you look at the uncertainties, you can see that at Gaia's faint end, Gaia and LSST overlap very nicely, and LSST then continues this roughly 5 magnitudes deeper. So there's a really nice scientific overlap here between the two projects. So I'll talk to you now a little bit about the data processing in Gaia and how we arrived at the science product. How did we go from this data, the telemetry, and to produce the data products that are shared with you in the Gaia Science Archive? The satellite and payload of Gaia are the responsibility of ESA. The data processing and the production of the final science data products are the responsibility of the scientists and the engineers, which are located in a large number of ESA member states. 24 countries, 160 institutes, and over 400 scientists and engineers comprise what's called the Gaia Data Processing and Analysis Consortium. The data from Gaia was distributed out to many of these centers where it was processed, and the data products were then sent back to Madrid, where they were exposed to the community through the Science Archive. And just to show a quick correspondence with LSST, LSST is also a distributed project, where here you have people working on pipelines, you have a data center at NCSA, and also at the IN2P3 in France. I'll just point out one difference between the LSST data processing and the Gaia data processing is that at the data centers, NCSA, and at the IN2P3, they run the same set of algorithms. They just run it on different data. Whereas within Gaia, the data was divided up and distributed through the data processing centers according to either the instrument or a science topic. So for example, in Cambridge, they did the processing of the photometric data. In Geneva, we did the processing of the variable star data. So that's, the algorithms won't all run in the same place, and these separate data products were then sent back to Madrid in Spain, where they were combined to produce the full catalog. So I won't go through all this in detail. I provide a lot of this information really for reference for people, but one thing that was very key in order to make this distributed project work was to have a common team that oversaw standards, conventions, and tools. And I'm sure that many of you will recognize at least one person in this photograph who was instrumental in putting together this. I'll just help you there. That's that person there. It's Will, the LSST data management manager. This was instrumental. The fact that all the data processing centers and the coordination units that did the science processing conformed to a lot of these sets of guidelines for things like common libraries for algorithms. For example, everyone didn't define the cosmological parameters separately in the data centers themselves. They used common libraries. We had common engineering guidelines, reference systems for Gaia. You know, which way is up on Gaia? What's a row on the focal plane? What's a column? Things like this. Release and configuration management was all centralized, with common code repositories, packaging for third-party libraries, and things like this. And having one dedicated team based in Madrid to oversee all of this and set standards for the data processing centers meant that all of DPAC, all the data processing centers started out on the same page, and then it became much easier to integrate these subsystems when the data were moved back to Madrid. Communications. Clearly, with such a distributed project, communications were very important. Things like weekly meetings between the coordination units where the scientific processing was done and the data processing centers, wiki pages, project newsletters, and things like that. One thing that we didn't have was a Slack-like tool for the whole collaboration, which LSST has, which I think is a really excellent tool, and it really facilitates internal communication in LSST. I think it would have been great if we could have had that in Gaia. However, Skype was used, although it was not a standard, but many people used it, and it was used extensively during the operations rehearsals, which did help to pull people in disparate sites together during operations. We didn't have any collaboration meetings like this one until after the first data release, which is probably a bit unfortunate, because they turned out to be a great forum for people to interact in and to discuss interfaces. And there are a set of liaisons were set up between the different processing centers to ensure that interfaces and requirements were understood and well communicated. And so you show two people in Gaia who are discussing, I think this is during operations how to get the operations rehearsals running. Towards the community, during the commissioning period and before the data releases, the community were obviously very excited and very impatient to see what was going on. We had many ways of communicating to the community. There's a Gaia blog, a Gaia app you can install on your phone. There's obviously a Twitter feed. Something very interesting was something that was called Image of the Week, where scientists internally in Gaia could ask for a particular product they'd been working on that they thought was ready to show to the public in a sort of unofficial way, a non-refereed way, but as an interesting image. And one of these came out every week, which showcased the progress of Gaia and how things were moving forward. Science management. So it's not an easy task to manage 400 scientists and engineers distributed across the whole of Europe to write millions of lines of code over 10 years. I wanted to point out a few of the things here that I think are crucial in terms of the management of science projects to achieve this. The data processing centers were all very independent and they were free to choose their own technologies. Some used databases, some used MapReduce type approaches. What was able to hold things together was having a set of well-defined interface control documents that each of the data processing centers would conform to. Locally, they could treat the data how they wanted, but they had to confine to these interfaces for the data. Things like clear procedures for software configuration and developers for interfaces to code to. Just one point I'll make is about, I think, an emerging profile called a research software engineer. These are people who are very good software engineers, but also have very good domain knowledge. And we found in Gaia that this sort of profile was invaluable in being able to understand what the science was that we needed to do, but also to understand the technical aspects of implementing these complex pipelines to process billions of stars. In terms of communications, really science and integration teams, science and technical teams, they have very different priorities. The scientists always want to improve things and implement the newest algorithm, and the engineers always, they need stability in order to integrate things. And so this was always a bit of a clash, and finding that middle ground whereby you could still develop but yet deliver a product was quite challenging. It's also not obvious to a scientist what is obvious to an engineer, and vice versa. Often you would find that there was a different language that was being spoken, which sort of comes back to this point about how the research software engineer profile, these people in Gaia were invaluable in understanding the science, but also understanding the technical aspects of the project. And so here you see a picture of the spectroscopic processing group. These are the scientists and the engineers from the data processing center thrashing out the radial velocities just before the release of Gaia Data Release 2. This was in Paris last year. Operations rehearsals. I can't stress enough how important it is to start rehearsals and integration before commissioning. Gaia ran about 4 operations rehearsals with simulated data and with Gaia data. And in the beginning, many things did not really work very well. They fell apart, they were hard to get going. And it's really important to start these sorts of things early. As well as identifying defects, obviously missing functionality, assumptions, validating requirements and technical interfaces. It also helped, these operations rehearsals also helped to bring people together to transition the mindset from that of an independent system testing mindset to building an integrated system that should work and function together as one, and really helped to sort of cement protocols and communications between teams. So again, early integration testing is absolutely crucial. Okay, the Gaia data releases. Release early, release often, but not too often, because it's a lot of work. One thing I'd like to stress about the data releases is that the Gaia data are released in a series of intermediate data releases. So the final release is not out yet. And each of these intermediate releases should represent a scientifically significant step forwards. And I show this picture here to show you, here is the parallax uncertainty of Gaia data release 1, and here is Gaia data release 2. And you can see that there's been a massive improvement in the quality of the data. And that with Gaia data release 2, in fact, Gaia is already quite close to achieving the 5-year performance. So this is a very important point with data releases, not to just make a release for the sake of it because you have more objects, but what new science can you do with your data? How does this, what advancement does this represent scientifically? A data release, however, is not just producing the catalog and the science data products. It also involves a long process of verification and validation and of the dreaded documentation. People never like writing documentation. And in Gaia, this included refereed papers, online documentation, which described in great detail the calibration models, the processing steps, and then things like archive metadata. Don't forget, you also have to have units, types, data types, information like this in the archive, and this is also documentation. A few quick points on the verification and validation that we did in Gaia. Each one of these coordination units and data processing centers across Europe would run its own internal system-level validation. Gaia also had one dedicated team based in Madrid that would then perform consolidated full catalog validation campaigns on the whole integrated system. And this involved working quite a lot within the science community within the Data Processing and Analysis Consortium. It was an iterative process, going back to the subsystems quite regularly to try to understand discrepancies and issues. And I would say it probably took about 3 months before the release of the Gaia catalogs. So this was the validation of the catalog. Something else that Gaia did was to release a set of performance verification papers. And these are refereed publications. You can find them in journals and also on the archive. The goal of these papers was to demonstrate the science quality of the data through examples. And they provide a short introduction to selected science topics that attempt to showcase what science can you do with this data release. They are not an in-depth analysis of this subject. And there's just a couple of examples here. This is the solar system objects, and these are some HR diagrams that can be produced with Gaia. I'm going to skip that a little bit, yeah. So online documentation, this is quite important to have in addition to the publications because it provides detailed explanations of the processing, the calibration steps, and it also instructs the users, the scientists, on how they should use the data, what the limitations are, and what they need to look out for when using the data. It's very difficult to motivate people to write this documentation, and one solution to this in Gaia was to have this online documentation indexed in ADS so it could also be provided as a sort of a reference when people, on people's CVs when they apply for jobs. Okay, and so the final topic now I'm going to cover just in the last few minutes is constructing a petascale science archive. Like LSST, Gaia will be serving up petabytes of data to the community, and this just gives you an overview here of what the Gaia Archive, or some of the features that the Gaia Archive provides. With every data release catalog, you get these all-sky summary statistics, so every user doesn't have to go in and build these themselves. You think things like distributions of radial velocities, a parallax histogram. You have interactive plots here where you can have a look at the Gaia sky, hone in on a source. You can get the information about the ID and its position. You can then use it to generate queries to search directly in the archive and go to Simbad, things like this. It also provides these all-sky plots of distributions of source density and things like that. These are all provided internally within the archive. The Gaia Archive is moving towards what's referred to as a code to the data model, whereby you don't download the data, even though you can. There is a download function, and the data sets are currently much smaller than what the final data set will be. But they're also providing interfaces for people to run code and queries on the archive itself. So just out of interest, some figures about the usage. In the first 24 hours after Gaia Data Release 1, there are over 10,000 users. In the first week, there are 34,000 users. And you can see the profile here. And that's just Gaia Data Release 1. But as of June 2018, this has sort of settled down to a steady state number of about 500 or so per day. And you can see the distribution really is global. The US is, I think, the second biggest user after Germany of the Gaia data. The archive size today is 1.6 terabytes, and the final estimate is a 1.4 petabytes. Just a distribution here of the downloads that have happened per month. This is Gaia Data Release 1, so you see there was a big spike here, something like 75 terabytes. This then, after the excitement of Data Release 1, this settles down to a nice sort of steady state, with an enormous spike again for Data Release 2, as you can see. And I think that with LSST, we will see a similar sort of profile, if not, the numbers obviously won't be the same, but the profile, I think, will be quite similar. That there will be a lot of interest peaked around the intermediate data releases. User-generated data products. This is something, as many of you know, we are committed to providing, to supporting in LSST. The Gaia Archive provides an interface here. You see an ADL query that creates a set of tables, and these are user tables here, where a user who logs onto the archive can create their own user tables of data. They can share this with their collaborators who are also part of the Science Archive. They can use this, they can export this to tools like TopCat to produce plots and so forth. just an example of some numbers about these user data products. This is the number of user workspaces. And, sorry, this one, the top one is the user archive data, the amount in gigabytes, the volume in gigabytes, and these are the number of user workspaces. There's a little spike at DR1, and it steadily continues to increase over time, and then suddenly with DR2, you see another great spike again. And I think we'll see also with the user workspaces on the LSST Science Archive, people will be continually analyzing the data, slowly learning more about it, getting used to it. Probably, it peaked a little bit here, probably because people were preparing for data release 2 by going back and using data release 1. And just finally, I'll just show you some access patterns from the Gaia Archive. These are the number of queries received per month. It was quite small at the start, something about 1 million or so there with Gaia Data Release 1. And it built up to Gaia Data Release 2. In the month that Gaia Data Release 2 was released, there are over 3 million queries per month on the Science Archive. So these are quite impressive numbers, and this is already only the second intermediate data release, representing less than half the total Gaia data set. And I think that these plots and these distributions are very interesting for LSST, that we can learn a lot, I think, about building our science platform, our science archive, by working with Gaia to understand the sort of user patterns, how users work with this archive. And so I'll just wrap up now by saying that Gaia and LSST are two exceptional and very complementary surveys, both of which will have a profound impact on astrophysics for many, many years to come. Thank you.
So I'm guessing that the software, the data processing software in particular, that was on board the spacecraft itself was not part of the consortium that did the data analysis. If that was the case, did you have any different kinds of issues integrating with them and making sure that your interfaces with them were, and then the code did what you expected from that perspective?
I might delegate that to Will, because I didn't have anything to do with the ESA, the connection. This is the interface with ESA itself, but
let's say that the original algorithms were produced within the consortium. They were recoded for the onboard software by Astrium, because Astrium do that. Did we have problems with the interface? Not really. The spacecraft control interface is very well defined in terms of packets. Those packets with what stars go in what packets was defined. That's what you get down. So how it's processed, in fact, you don't care. And it worked extremely well pretty much out of the box. I think we were all kind of a little bit shocked when we turned it on, started spinning, we switched it on, and well, star packets came out, and they were pretty centered, and everything was not too bad.
So I was wondering if you have any thoughts or if you learned any lessons that are relevant for us in the fact that, like LSST, Gaia had no proprietary period, and how that worked for people who actually worked in the project for many years, and what you could do to make things positive for those people also.
For the people who worked in the project, yes, I do. So there's no proprietary period. People who worked in the project weren't allowed to do science with the data before it was made public. But obviously, people who were interested in science did start to do some preparatory work and think about what they were doing. Once the data was public, people within the project did start to publish data based upon the public data releases. The real problem, I think, for people working in the project is that as soon as the first data release was out, they were straight back onto processing the data for the next data release. And that's what was very challenging. In fact, several people have said this to me, and I know it myself from my own experience. It was almost impossible to find time to start working with this public data because you were straight on to processing the data for the next data release. So that would probably be the biggest complaint about people in the project.
Maybe a connection to my question, which is that, as scientists have started to dig into some of the Gaia data, there have been questions that have come up about, why do the algorithms select these objects and not these objects? Why is my favorite object missing? What is the selection function that's happening in the detailed processing? And trying to understand how to get visibility into that. So can you comment on, how Gaia and by extension LSST can, manage that communication with the science user community that I was very curious about the details of the algorithms that are implemented and trying to understand how that works.
Oh, it's gone. All right. So it's okay. It basically comes back to the release documentation. This is exactly the goal of the release documentation, as opposed to the refereed papers that are published in journals. It's also somewhat the goal of the performance verification papers. So if you have a look at the release documentation online, you go to the archive, you click documentation, it will take you to all the online release documentation. And here you have very detailed descriptions of the calibration models, the processing algorithms, the assumptions that were made. And this is meant to inform the science user of exactly the sort of thing that you're asking about. At this intermediate stage, clearly everything's not complete yet. So these algorithms will continue to be improved. There will be more algorithms that will be brought in. I mean, I can tell you that in the variable star processing, there are many more types of variable stars that we intend to process, but they just haven't been done yet. For the simple reason that the data set so far is not necessarily the best, or there's other data that you can get with that beforehand. So there's cases of prioritization as well of what you can do with a partial data set.
Hi, LeAnn. Did your operations rehearsals push data all the way to users or pseudo users?
No, we didn't go out to users. Users in the sense that there were scientists within the data processing and analysis consortium, but that was all. So we had a validation group within the data processing and analysis consortium, and many of the people in these coordination units around Europe were, scientists, professors, lecturers at universities, and so they did get involved, but not outside of DPAC, no. But we did have a good team within DPAC to do that.
Let's thank LeAnn again. So we have one final talk this session. It's going to be given jointly by Sarah Bro and Jim Bosch, and it's on deep blending, and there'll be a deep blending workshop, I guess, at this meeting.
So hi, it's a pleasure to be here this morning to have a chance to introduce the blending workshop that we've been organizing to take place within this broader LSST 2018 meeting. So, do you want a laser pointer? Yes, please. Thank you. Cool. So the aim of this quick talk is to just introduce the workshop to you, and given that many of you are very busy and have many different things to achieve at this meeting, give an idea for those of you of what's going on and how to get the most out of this blending workshop, even if you can't attend all of the sessions. I should add that the workshop's supported by the LSSTC Enabling Science Program. And actually, just anecdotally, I'd be really interested in seeing a show of hands for those of you who actually only came to this meeting because you were interested in the blending workshop. Now, don't be shy. Okay, so there's a scattering. Yeah, okay, that was interesting to know. Thank you. So anybody who's organized a workshop knows that you must have some ulterior motive to do it. I was here at this workshop last year and was hearing about images in LSST, and that the LSST would go deep enough, it would start to reach the confusion limit, that it would be deep enough that disentangling the different galaxies, the different stars, is actually going to be a challenge for the LSST images. Now that becomes something that kind of perks up my interest. My science interest is in the intra-cluster light. Now, for those of you who don't know what that is light coming from, it's very diffuse, really faint light coming from stars that aren't really bound to galaxies floating around the center of galaxy clusters. And this is one of the poster images for this light. This is an image of a very low surface brightness, a very faint image of the center of the Virgo cluster taken by Chris Mijos in 2005. And in this image, these big white things, those are galaxies in the cluster. But around those, you can see this orange to red, this faint, diffuse starlight, which is coming from stars that are 1,000th of the brightness of the night sky. So to be able to see those stars and kind of measure those in great detail requires you to really understand your images, which is one of my drivers for wanting to organize this, this workshop. There's another driver. So this is a more recent image. This is from, this is archival data from HyperSuPrimeCam. It's a much more recent image. It's 240 seconds. Has some imaging issues that we would take out by combining images, so ignore those. But I'd like you to draw your attention. These are just a few I just saw by eye of galaxies. These are all galaxies, apart from the great big star. These are galaxies that are blended together. It's really hard in this image. Like, how would you make out in an automated way the brightness from this object versus that object? And especially when in the same image, you also have a great big grand design spiral with lovely great star-forming knots. And you don't want to divide that galaxy up into its knots. You want to hold all of that together. So how do you simultaneously achieve all of those things so that you can see the low surface brightness light that actually you can't quite see but is sitting in this image, and find your high redshift lensed galaxies, and all of these things all at the same time. So it's, I have my picture here. I think it's turtles all the way down is a fairly good analogy of the images that we're going to be looking at. So who is doing this? As I said, this is actually an issue. It's a problem for all of the science collaborations, from solar science up and out to cosmology. So I've been working with Pat Burkett and David Kirkby in the Dark Energy Science Collaboration, and Alexei Lotho as well. And we brought together a group of scientists from across the science collaborations in LSST. We really wanted this broad representation to find out about how these issues affect everybody. And people italicized here are those who are present at the meeting. So what is the workshop made up of? Well, first of all, it's going to be held in the Presidio 3/4 room. So that's where we'll be when you're able to come and see us. The sessions, we're going to start the session after the break with an introduction to the challenges and current status and future plans that exist already within LSST data release pipelines. And then I've highlighted session 2. This is the one I'm organizing, so I'm slightly biased. But this is the one where each of the science collaborations has a chance to give a really quick overview of how blending affects their science. So hearing from the different science collaborations on the same kind of outline, how does this issue affect you? Go through, discuss those issues, and try and bring those together. And then there'll be a tutorial session where we can actually kind of play with some data and look at how we blend, deblend within DM. Tomorrow we have 2 formal sessions looking at new concepts that people have developed for object detection, as well as tools and data sets for developing and evaluating algorithms for distinguishing these targets. Then there's also the Wednesday, the afternoon unconference session that Rampal's been telling us about. Many of you will have your ideas for things to discuss during this session. It's also a place where those of us from the blending workshop, if there are ideas that come up that haven't already been discussed, we can place things in that session too. Then on Thursday, a couple more sessions, one about clues that we might be able to take clues from the existing object catalog to find out about blended targets, and look at solar system objects in crowded fields. And then close out, again, I've highlighted this one. I think if you could only attend 2 sessions, that how do the blending issues affect the different science collaborations, and the workshop closeout where we try and close the loop, see how we have found out ways that these issues can be solved for different collaborations, but what needs to be done in the future and who needs to do what. It will be the subject of session 8, the workshop closeout. So just to workshop session 2, this is the outline, the agenda. Both these slides and the workshop agendas are online on the project webpage. So if you're interested in just turning up for your science collaborations bit, this is the order that these presentations will happen in. And then there'll be a significant time for discussion throughout this workshop. We want to hear people's ideas and thoughts. And the expected outcomes will be an inventory of the challenges that the different science collaborations face, identified overlaps between the science collaborations, and ideas for the unconference session. We're also, the Dark Energy Science Collaboration Blending Task Force have also been having kind of presentations for the last 18 months or so on blending issues from various people in the community. They have kindly made those presentations public to attendees of the workshop. So feel free, those are online, please feel free to go and look at those. You can, if you can't attend any of the workshop, you can look at the slides and the videos for these sessions. And for workshop session 3, this is a hands-on deblending tutorial. For those of you who weren't in Slack Club yesterday or and don't have an LSST identity, you'll need to go to the identity.lsst.org/that and hit the button for register a new user to have an account to actively participate in this tutorial. If you haven't had a chance to scribble down that link in the last 5 seconds, these slides are all online. You can just join the link from the slides. And allowing me to hand over to Jim, this is a beautiful picture of the kind of depth of galaxy image and some of the kind of issues we're going to be facing in terms of confusion.
Just a quick word to allay some of your fears about this image. This image is actually deeper than the Deep Wide Fast survey. It's not as deep as the LSST deep drilling fields will, but it is a bit deeper than the 10-year Deep Wide Fast, but not a lot deeper. So let's see. So, okay.
It's not on the laser.
Not on the laser burn. Okay, either way, I can do that. Alrighty, so before I dive into talking about what we on the project on the DM side of this want to get out of the blending workshop and how you should think about how the science community interacts with DM on blending, I want to go over a bit of terminology because we have a tendency to go straight into jargon on this topic. When we say blended, at least what I mean is that there are 2 or more objects that are close enough together that you cannot measure them accurately independently. And that makes it a much harder problem than if they were isolated. A detection, usually what I mean by this is that, say, given some images of some patch of sky, I want to return some above threshold regions and peaks within them. It's a slightly more precise thing than you might be used to when you hear the word detection. That's what I tend to mean and what other people in the project and DM will tend to mean. When I say deblending, usually I mean given detections, given those above threshold regions and peaks within them, separate the flux so you can perform a measurement on the objects as if they had been isolated. However, there's a second definition of deblending, which means deblending plus detection. So you have to be careful whenever anyone says deblending that you be careful clarifying exactly whether they mean detection as well. Certainly, the process of figuring out how many objects there are in an area is something you would naturally consider to be part of deblending. But typically, we also say that that's just part of detection, and the deblending happens later. All right. That said. I think it's fair to say that most deblending happens in pipelines DM runs in code DM nominally writes. And I'll unpack that in the next couple slides. But I want to then say, and this is paraphrasing Robert Lupton, deblending is intrinsically impossible. All right? It's one of our most difficult algorithms, both for development and for testing. And there's a broad range of classes of algorithm to consider. So there's a big scope of areas that we could try different things. But we don't have any simple ways to know when we've done a good job. All right. You can try running your deblender on simulations, but what you learn is only going to be as good as your simulations. And it's hard. This is an area where it's really hard to come up with simulations that really accurately reflect what the difficulty of the true problem. And if you do it on real data, you can't know if you did anything right. So I think the only way to catch the more subtle problems with deblending is to actually try to do high-level science analyses. And there you'll notice, well, this curve doesn't look the way I expect. Could there be a reason could the reason be something in deblending? It's also true that a lot of our outputs are going to involve multiple mutually exclusive interpretations of the data. We will say that, well, you could think of this patch of sky as being 3 objects, or you could think of it as being 1 object, and we'll probably provide measurements of both of those interpretations and possibly more of them. And so to use our catalogs properly, you need to know which of those interpretations you want to pick, which one's more likely to be right for your science goal. So before I said that most deblending happens in pipelines DM runs, and the exception here is that there are going to be some classes of blend that we just don't handle well. And I think these are going to include things like strong gravitational lenses, supernova light echoes, galactic cirrus, messy galaxy mergers. These are rare things that what the right answer is even more dependent on on what science case you're doing, or more specific. And our goal for these kinds of things is to do well enough on them that you can find them and then do your own custom processing later. And we're going to try to focus our efforts on making sure that blending works well enough for more common kinds of objects. So if you're interested in working on algorithms outside of DM, and you're in one of these, if you care about these classes of objects, you'll definitely think about writing your own tools to process images after DM is done with them. I also said that the deblender is code that DM nominally writes. The caveat being that if the community writes a better one, we'll absolutely use it. It's our job to write this, but we're not going to be blind to things that are developed outside of the project. And in fact, while the current deblender was written by DM, this is something that was derived from the SDSS deblender, where that algorithm worked pretty well. It's been used in all the HSC data releases to date, and it's known not to be good enough at LSST depths. If you give it an image like the one we showed you earlier, the isolated things turned out okay. The not as isolated things are a little bit worse, and the things that are really, really crowded are generally horrible. And that's a big problem for people who are, say, looking at those galaxy clusters in that image. The deblender we're integrating and evaluating for the future right now was partially written by DM. This was a collaboration between Fred Mulkamp and Peter Melchior. It's called Scarlet. You'll be hearing about it more, of course, across the week, especially if you attend the blending workshop. We don't know yet whether it's better than our current deblender yet. We expect it to eventually get better than our current deblender, but it's also not the only thing on our radar. There are some other efforts, especially in DES, that we're looking at where they use a totally different approach that may be something we'll want to adopt as well. So the DM's goals, my goals for the blending workshop, I want to help the community predict what blending and what DM deblending will do to the astronomical objects that the people in the science community care about. I want to encourage and enable the community to help in evaluating Scarlet. I think as I said, we don't know when we've done a good job, and it requires a lot of people looking at it from a lot of different angles to know when a deblender is doing a good job. And I think it's an accessible enough piece of software that a lot of people outside DM can get their hands on it and try it and see what it does to their science. I want to make sure that the DM deblending plans stay consistent with what the community wants. And I want to make sure that that there is feedback from the community, that it's done and that work is done in a way that can feed back into DM. That's all I've got. I hope you attend the blending workshop if you're at all interested. There's sessions essentially for every single breakout session until Thursday, and I hope to see you there.